All right, now I want to turn our attention to fixing a multiple regression model when it looks like the assumptions are just violated. So in the simple linear regression context, our strategy was to employ transformations, try all transformations of x and y to try to find a relationship that was linear between them. Now, in the multiple regression context, it's a bit trickier because sometimes there might be linear relationships between y and some of the predictors and nonlinear relationships between y and some of the other predictors. And so employing polynomial models is one way to fix the curvature with particular predictors. Okay. So what is a polynomial model? Well, we're going to say that we have a polynomial in x if we have the following terms in our model. Basically, we have x, x squared, x cubed, all the way up to x to the mth power. The degree, or the order of the polynomial, is called m, and it's just basically a weighted sum of the powers of x. So what's the use of a polynomial model? Well, a polynomial model actually gives very flexible looking curves. And in fact, polynomial models can even fit non-monotonic curves, which is the only thing that we've talked about so far that allows us to approach that sort of relationship. So here are three examples of polynomial curves. We see something like x squared, where it's increasing more rapidly as x gets bigger. Here's an example of a second degree polynomial, 1 plus x minus 4x squared. It's curving downwards. And here's an example of a non-monotonic polynomial, where we have an increasing part and a decreasing part. This is 1 plus x squared minus x cubed. So as you can imagine, based on what the coefficients of the powers of x are and how many powers of x I include, I can actually get a very flexible shape for what the relationship between y and x might actually be. So when we see some sort of curvature in the predictor versus residuals plots, we can apply a polynomial model to try to fix that. So let's just look at some examples here. We've seen an example with the bulldozer data set. Here I've already fitted the bulldozer model here predicting sale price from all the predictors in the data, the sale date, year made, machine hours, blade width, and tire size. And if I run check regression on the bulldozer model, I see a very tragic looking residuals plot. I see some sort of curvature, which indicates there must be a nonlinear relationship going on between y and at least one of those predictors. So if I check to see the residuals versus predictor plots, the one with sale date looks fine, but the one with year made looks very curved. So there's a nonlinear relationship going on here, and so that's a prime candidate for employing a polynomial transformation. The other residual versus predictor plots look just fine. I don't see any sort of curvature. Another example is with the cars data set. And the cars data set is one of the Chapter 3 data sets. And what I've done previously here is I've fit a model trying to predict the fuel efficiency from all the variables in the data, the size of the car, horsepower, top speed, and weight. And if I were to look at a scatterplot matrix of this data, let's bring that up, we see that there are potentially nonlinear relationships between y, the fuel efficiency, MPG here, and maybe horsepower and top speed. I do see some sort of curvature. Let's actually look at the residuals plots to see if that's still an issue. Well, in the residuals plot itself, this looks actually pretty good. I don't see any sort of curvature going on. I see equal spread, and I actually see normality pretty well going on as well. So these plots don't indicate any sort of problem. However, if I continue and look at the residual versus predictor plots, once I get to the one with horsepower, which was one of the ones where I saw curvature, I do see a hint of some sort of curviness. Now, how do I pick this up? Well, on the far left of this plot, I see points above and below the horizontal line, so I see positive and negative residuals. But there's this pretty big chunk right in here where all the residuals, or all but one, are positive. So that's why I'm really picking up this sort of curvature in here. With top speed, I see the same sort of issue, where wow, this big chunk where all the residuals are positive, it looks like the residuals might actually be curving up or something. So this stuff actually does happen in the real world. Sometimes there are curved relationships, and the polynomial model, fitting a polynomial model with those predictors, can be the solution. But the question that we need to answer is, how many powers of x should I really be including? Do I need x squared, x cubed? What is the order of my polynomial model that I should be fitting? The highest power of x in my model. So how do we determine this? Well, one thing we know we can't do is look at the r squared of the model, because we know that r squared always gets bigger whenever I add in a new predictor. In other words, if I were to add in a higher power of x, even if I don't need that higher power of x, r squared is always going to get bigger, because adding in a new variable gives the model a little bit more wiggle room, and it's going to fit the data better. The sum of squared errors is going to get smaller, r squared gets bigger. So instead, what we're going to look at is the r squared adjusted of various models where I've included a bunch of different powers of x. Remember, r squared adjusted is better than r squared because it penalizes r squared based on the complexity of the model, how many terms are in there. R squared adjusted is only going to get larger if the new variables that I'm added really do significantly help me predict y better. So there's a command choose.order, which we'll run. And what that is going to do is it's going to spit out a list of powers that have been included into the model along with the r squared adjusted. So typically we're going to look at a maximum order of 6. So I majored in physics and astronomy. I've seen a lot of equations that are out there describing the real world, and I've never actually seen an equation that has a power that's higher than 4. So remember, one of the goals of regression is to come up with a model that accurately reflects reality. So it's kind of unrealistic to try to fit a polynomial model with a really, really high order, because the real world doesn't really seem to work that way. I'll allow it to go up to 6 just for kind of probing and illustrating things, but most likely we're going to choose a very low order polynomial, maybe 2 or 3 at the most. So we're going to look at the r squared adjusteds for each of these models with all these powers of x. And most likely there's going to be many that have comparable r squared adjusteds. So I could just blindly choose the one with the highest r squared adjusted, but I'm not going to quite do that, because when I'm building a regression model, I'd really like to come up with a simpler model if at all possible. So what I'm going to do actually instead is to choose the simplest model, the one with the smallest order, that has an r squared adjusted that's not too much worse than the overall best that was seen. And my guideline that I've come up with, and this is my own, you won't see this anywhere else really, but I think it's pretty useful, is I'm going to choose the simplest model that has an r squared no more than 0.005 below the very largest that was observed. So going back to this bulldozer data, if I fit just a simple linear regression predicting sale price from year made, I know I'm going to have curvature here, and I run my command choose order, it gives me the list of orders, the powers of x that it's including into the model, and then also the r squared adjusted. So I see I get a pretty big leap from just going from year made by itself to year made plus year made squared. It actually goes down a little bit when I add in a third power of year made, and it starts to increase again when I add in the fourth and sixth power of year made. So, okay, out of the 6 powers here, this one is obviously the largest. However, I can get away with actually doing a simpler model that doesn't give up too much in terms of r squared adjusted. So my guideline is to calculate what is 0.005 smaller than this, which would be 0.576. And I'm going to choose the simplest model that still has an r squared adjusted larger than that, larger than 0.576, which would be a second order polynomial. So it looks like I really only need to have year made and year made squared into the model. And in fact, when I do that and plot what the resulting curve is, it looks like it fits the trajectory fairly well. And if I look at the residuals plot to that, I don't see any sort of leftover curvature. So looks like an order 2 polynomial, year made and year made squared, is sufficient for describing the curvature in the stream of points. I don't need to add in that 6th order polynomial because that makes the model a bit too complex. Sure, it has a slightly higher r squared adjusted, but I'm not really giving up all that much r squared adjusted by going with a vastly simpler model. So I could do this with the automobile data set. Let's actually just do that right now. let's fit a model with horsepower, because we saw that had a curved relationship. And I'm predicting MPG from horsepower in my car's data. And let us do the find order command on this model. So, of course, I typoed it. I always forget what the name of my functions are. So I will go and look at library reg class. What is the name of the model, or the name of the function here? So it's choose order, actually. So I can input in the name of my model, choose.order. By default, it's going to probe orders 1 through 6. I could do something more complex, like up to a 12th order polynomial. I'm never going to do that because I know that's not really the way the real world works. And so what I can look at is, well, what's the highest r squared adjusted that I see? And it looks like the 12th order polynomial is actually the highest r squared adjusted. I know the real world doesn't work with 12th powers, so what I'm really going to do is I'm going to look for, oh, no, I'm completely wrong. 0.834 looks to be the best. So the absolute highest r squared adjusted is 0.834 with a 4th order polynomial. What is 0.005 smaller than that? Well, let's calculate that value. So I'm going to choose the simplest model whose r squared adjusted is at least 0.8294. So, okay, well, it turns out that the only one that has that is the simplest one is the 4th order polynomial. I can't quite get away with the 3rd order polynomial based on what my criteria is. So I'll stick with that 4th order polynomial. Okay, and I can kind of just see what that looks like. Let's plot the relationship between fuel efficiency and horsepower. And the way that I'm going to fit this model is, and we'll learn more about this later on, is I'm just going to say poly. That's going to make it a polynomial model, poly horsepower 4. And what I'm going to do is I'm going to add the fitted value so I can observe this curve. So I'm going to add the values of the horsepower. So don't worry too much about the syntax. We'll learn that a little bit later. I'm going to make this in red. And so I see my 4th order polynomial seems to really match the trajectory of that stream of points. And if I were to check the regression with this 4th order polynomial, I get a little bit of an error here. I'll have to figure out why that's the case. But this residuals plot looks brilliant. So that is one thing that we can do when we do see curvature in the predictor versus residual plots, is to try a polynomial model. Okay, so we'll talk more about how we deal with polynomials a bit later. One thing I do need to mention, however, is something special that we do with polynomial models. So we've talked about in a multiple regression model, it's okay to drop a single predictor from that model if its p-value is bigger than 5%. Because what that p-value is describing is the significance of the reduction in the sum of squared errors when that particular predictor is added to the model that already has everything else in it. So it's okay to drop that one predictor if it's not significant. We can't drop more than one because p-values are model dependent, and any other non-significant predictor could become significant once something's eliminated. When we deal with polynomial models, we're going to behave a little bit differently. We're not going to drop any of the powers of x after we've chosen the order of the polynomial. So we're going to keep all powers of x regardless if they're significant. And it's really, when we talk about descriptive modeling, the order of that polynomial model that is more interesting to us. So if I were to look at the summary of my 4th order polynomial model, predicting fuel efficiency from horsepower, I've decided I've chosen the 4th order polynomial, so even though this guy's not significant, the 4th order is not significant, I'm still going to keep it. Okay, so a little bit of extra consideration for polynomial models. Next up is interaction variables.